All right, continuing on with class 13 or week 13. We have a rotational example with a slightly different approach. I believe these are from Dr. Bob's notes. We're going to have mass moment inertia J2 and J1, and then there's a torsional stiffness that's between these two possibly rotating disks on this fixed to the shaft. So we got the mass moment. We take the sum of the moments of let's say this. Call this an FBD right there. And so this torsional stiffness times the change in angles is, if we abide by counterclockwise being positive, would be that J1 times theta 1 double dot. And the same thing for the other. Let's call it. No, we're just rewriting that out. I'm sorry. That's just rewriting it out onto one side. And if you take the other FBD, and we would presume that we would also have an IBD, that'd be nice to have, but not in this case. And write out fill those out. Noting again that we have an equal and opposite, right? So this guy right here, he's in one direction, he's positive here, and on one FBD, but he's equal and opposite on the other FBD right here, so he's negative. And we have another equation. So we have these two equations, and we can assemble them into a matrix, two matrices. The J matrix here, or the mass matrix, the inertial matrix here, and then we have the stiffness matrix over here. And notably, this diagonal, they can be varying things. They just happen to be the same. But what we'll often have, and we should check for, is symmetry about the off diagonal pieces. That's be a very common case for those to be be symmetric. So we assume it's the solutions of the form there, and so we can plug those in. Plug in with this assumed format. And distribute these. All right, so this is just a slight variation of what we've done previously, and we want to find the determinant of this combined mass stiffness matrix. And when we do that, we didn't bother doing the substitute with the lambda. I think I prefer to do that personally. This is just different notation. Also in this case, by the way, because it's a simple, I can explain a little bit why this is sort of an overly simplified case. This thing doesn't have any restraint to the ground, so it's sort of free floating. There's no boundary conditions to it. So that's it. And when that happens, when there's a translation possible, we will often have one of the natural frequencies be 0 right here. So here we go. Here's the only real natural frequency is this omega n2 for those two eigenvalues. And the eigenvectors, what we could do is we could plug in omega n into here, and what we just have is sort of a nothing burger, right? Where we just say that they're going to move together. Their A1 to A2 ratio. So just plugging those into there. And then if we plug in this other solution into that equation up above, we can find that we get the ratio of the amplitudes is dependent on, of course, they're going to move in the opposite direction, but they're the amplitudes are related to the mass moment of inertias, right? So that was one example. So well, I guess there was two examples in here. We're going to do some more. I would very much encourage you to go to the course website and work through these other equations, which I've also done with you. So in here, check out these suggested problems. There's really only 3 of them, although there's 4 of them, because there's an n times the k right in there. So the first one asks us to do a general. No, the first one asks us to find it when n is equal to 1, and the next one asks us to find it when n is just it remains an integer, right in there. And then I would suggest that you look at the solutions that the book has, but also check out my solutions. What I prefer that you do, especially in the part where you formulate this, we will have a quiz on these, right? So don't make sure you try them yourself. My scanning app is not doing great right here. I think it might be a reflection. Anyway, hopefully that's helpful in your preparation for the quiz.